All right, section 5.4 on inverse trig functions, so inverse trigonometric functions. A little bit shorter of an assignment this time. Hopefully it'll go quickly as well, though. Solving basic equations on an interval, so basic trig equations. So a basic trig equation is just sine of theta, cosine of theta, or tangent of theta equals some constant. So we're going to be asked to solve these equations, but we're also going to be given some interval. So we want the angles theta that are in this interval and satisfy the equation. Okay. So for these basic equations, it comes down to simply memorizing the table or being able to look up on the table. So we are looking for an angle that has a small y coordinate. So this is my memory technique. This would be small y. This would be a shallow angle. And so the theta would be, it looks like we're supposed to be reporting in radians, so pi over 6. Okay. And then to try to solve the other one, cosine is somehow connected with the x, so that we're looking for kind of a small x coordinate. To get a small x coordinate, we need to have a steep angle. And so the memory technique would be something like that. Again, if you just want to look them up, that's your prerogative. For sine being a half, the angle was either pi over 6 or 30, and for cosine being a half, the angle was going to be 60 or pi over 3. Okay, so the table is what's going to help us when the interval is from 0 to pi over 2. But now we're going to stretch this out, and we're going to say, okay, now what we want to know are all of the angles that satisfy sine theta equal a half, but in the interval from 0 to 2 pi. So we found one angle already. It was pi over 6. So the question is, are there other angles that have a positive sine value and a reference angle of pi over 6? And in fact, there is another one. Positive sine in Q2. And to have a reference angle of pi over 6, the other angle is going to be 5 pi over 6. So there was a second angle in the interval from 0 to 2 pi that satisfied this equation. Same thing here for the cosine. One angle we've already found in 0 to 2 pi. And the question, is there another? Okay, so we're trying to think about another angle who has a positive cosine and whose reference angle is pi over 3. And this winds up being down in Q4. So in Q4, for the reference angle to be pi over 3, the angle would be 2 pi minus pi over 3, and that's 5 pi over 3. So that's the second angle in this interval. Okay. I wish I had a tablet where I could draw those pictures quickly, but I'd be glad to do that in class. Okay, so the goal of this section is to be trying to define inverse trigonometric functions. So remember when we defined the log function to be the inverse of the exponential function, the idea is that the log was supposed to be the undoer function. And we want the same properties for the inverse of sine and cosine. We want them to undo sine and cosine. So what we've just seen here, the equation that we just solved, we saw that sine of pi over 6 was equal to a half. So if the inverse sine is going to be the undoer function, then we want the inverse of inverse sine of a half to get us back to the pi over 6. But the problem is that we also saw that sine 5 pi over 6 was equal to a half. So we'd also somehow like the inverse sine of a half to equal 5 pi over 6, because we'd like it to undo this thing as well. But we can't have it both ways. We can't have inverse sine of a half equaling both of these angles. So what to do? Well, we just make a choice. And here is a choice, it's a convention that people have settled on. So we're going to define the inverse sine to always be an angle chosen in this closed interval. Okay, so that's in some ways an arbitrary decision, but the mathematics world collectively has decided upon it. Right there, that's where the inverse sine will always choose an angle in this interval. So, congratulations to pi over 6. Condolences to 5 pi over 6. You are not the choice. Okay, so the inverse sine of a half is going to be defined to be pi over 6. Right. So we have the same type of problem for the cosine. In trying to define its inverse, we run into this problem. Like, hey man, we found two different angles that output a half. How can we undo that? Are we going to pick pi over 3 or 5 pi over 3? And this time the convention is we're always going to choose an angle that's between 0 and pi. So this time congratulations goes to pi over 3, and 5 pi over 3 misses out. Okay, so this whole discussion that's trying to motivate this blue box, which to my way of thinking just kind of gets dropped as a bombshell at the very start of the of the section without a lot of explanation. But this idea that we're going to define the inverse sine to always be in this interval is exactly what's in this blue box. It says the inverse sine, its range, that is its outputs, will always be in this interval. And for the inverse cosine, it says its outputs, its range, will always be in this interval. The full names arcsine, arccosine, arctangent for these inverse functions. Okay, so in words, I think it's important that you're able to kind of fill in the blank here. When you want to think about the inverse sine of x, what you always want to think about is that it's an angle. As strange as that sounds, it's the angle in some interval. And I guess I didn't get it scrolled off screen here, but it's the angle in the interval from minus pi over 2 to pi over 2. And again, that's just our convention. That's where we agree we'll always choose it from. Whose sine is x. And I could also say that if you want to use more equations than words, that satisfies sine of theta equals x. That's what it means when I say whose sine is x. Right? And cosine is, we just make this agreement that we'll choose the angle between 0 and pi. And then for the tangent, the convention is we choose the angle between, this one has to be the open interval. And I'm sure we'll wind up discussing that at some point, why that's open. But a central idea or central theme to always hold on to is these inverse trigs, be they sine, cosine, tangent, they're angles. You always want to think of them that way. They're angles. Okay. This is just the essence of that blue box. If you want to look at something a little tamer with fewer words. The inputs to the function and the possible outputs for the function. Okay. A very important word about the notation here. I should put a timestamp soon, but when we talked about the Pythagorean identities last time, we saw this notation where we had a square on the trig function, cosine squared, sine squared, tan squared, and that was shorthand for this, for the cosine of x quantity being squared. However, and this is another unfortunate potential confusion of notation. Cosine to the -1 here, first of all, you don't want to read it that way, but you read it as the inverse cosine, but it does not equal 1 over cosine. Okay, it is a completely different function. It's defined to be the inverse of cosine, so it's not 1 over cosine. It's the undoer function. Right? The inverse of 10 to the x was not 1 over 10 to the x, it was log x. Right? So just to show you that these are quite different, 1 over cosine of 0, well, cosine of 0. 0 is a flat angle. I want the x-coordinate. It should be big, so cosine of 0 is 1, and this comes out to be 1. The inverse cosine of 0. This needs to be an angle whose cosine is 0. Okay, so one of the angles whose cosine is 0 is the steep angle, the straight up angle. And there are other angles whose cosine is 0, but that's the one that we choose because it's in the interval from 0 to pi. Okay, so again, to try to compute these things, you either do what I do, talking about steep and trying to do it by memory, or you look them up. And an angle whose cosine is 0, you go to the cosine, you find it 0, and then you read off the angle. All right, so we're going to try to practice evaluating some of these inverse trig functions by hand. So if you're asked to find the inverse sine of 1/2, again, what you want to think about in words is that this is supposed to be an angle in some interval, and for sine, the interval is supposed to go from minus pi over 2 to pi over 2, whose sine is equal to 1/2. Right? So that whose sine is equal to 1/2, that means you got to solve this equation. And we've already done this. So this was theta equal pi over 6. And that's the final answer. I guess I should write it as the final answer. Okay. The inverse sine of -1. So an angle, again, this restriction is the same, minus pi over 2 to pi over 2, which satisfies sine theta equal -1. Okay, so you might, this is optional, but you might help yourself by thinking about an angle whose sine equals not -1, but just 1. Okay, so this is a steep angle. This is the straight up angle. So this would be straight up, pi over 2. So the angle that's giving a sine of -1 is going to be the straight down angle. So the inverse sine of -1 is equal to negative pi over 2. Okay, we'll try one more here. So an angle in the interval from 0 to pi, whose sine, whose cosine is minus √3 over 2. Okay, so this is a negative number, so one thing that you might observe off the bat is that this is going to be in Q2. In order for the cosine to be a negative number, we need an angle in Q2. So you might think about solving cosine of theta equal positive root 3 over 2. And this gives an angle, let's see, that's an x-coordinate. It's a big x-coordinate, so I want a shallow angle. This is pi over 6. Maybe I could put a hat on these. We could actually think about this as being the reference angle for the angle theta that we're actually looking for. Okay, so the angle that we're actually looking for doesn't have a cosine of positive root 3 over 2. It has a cosine of negative root 3 over 2. And that means it's in the second quadrant. It's in the second quadrant and has a reference angle of pi over 6. That means that the actual angle that we want is equal to 5 pi over 6. And that's going to be the answer to this problem. Ooh, 5 pi over 6. Okay. Right, I got to put in a timestamp because we've been going for 30 minutes. Oh, but maybe a shorter lesson today. We'll see. Yeah, this will be a quick topic here. So, frequently, or I guess up till now, in the right triangle problems, we've been finding or expressing sides in terms of angle length. And, oh, this is already typed in. I didn't realize that. And now we're going to turn that around. Now we're going to try to find the angles expressed in terms of the sides. So they're asking us to find the angle, again, like, oh, here it is. But we're going to numerically try to compute this angle. So this angle has opposite side 10, hypotenuse 50. So the sine of this angle should be 10 over 50, or 1/5. Okay. So what we're going to do now is use the inverse, the undoer function, the inverse sine function, to say, oh, the angle itself must be the inverse sine of 1/5. Right? So if we take the inverse sine of both sides, the inverse sine and the sine, they cancel, just as e, a natural log, did. And then you should probably try this on your calculator right now to see if you get this answer. Again, this could be a degree versus a radian issue. This numerical value right here is in radians. And if you want to convert to degrees, that would be the answer. Right, one more problem as a word problem. And then we'll have one topic left. So, lighthouse out here, it's 2 miles offshore. And let's see, express the angle formed by the beam of light and the distance d. Oh, I didn't see the distance right here, this distance d. So they're trying to get us to express the angle in terms of. So again, we want a formula for the theta. That's what it means. Theta equals something, equals some formula involving d. Right, so when I look at the right triangle, the right angle is here. I've got a theta. Its opposite is 2. Its adjacent is d. So that suggests we look at the tangent of theta. So tan of theta is equal to, what did I say, opposite over d. Right? So to find theta, we take tan inverse of both sides. And I'll do that as 2 steps here. Again, to try to emphasize the cancellation that takes place. All right, so tan inverse of tan, those cancel. So this is going to be not a number, I mean, but theta in terms of d. Here's a formula having d over here. Okay. Last topic then. we're going to compute the trig of an inverse trig. So an example might be the cosine of the inverse sine, or the sine of the inverse tangent. To do that, I'm first going to do a quick review here about this problem we've done in the past. We're going to sketch an angle whose cosine is 3/5 and then compute the sine of that angle. So let's see if I can do that successfully. I just needed to get a blank triangle here. So if you remember how to do this problem, you just draw a right triangle and don't worry about the scale, just label one of the angles as theta. And now we want to set it up so that the cosine of theta is 3/5. Let's see, the cosine is the adjacent divided by the hypotenuse. So there it is. That angle now has cosine of 3/5. We want the sine of this angle. For the sine of the angle, we need the opposite over the hypotenuse. So we solve for the opposite. We get 3 squared plus opposite squared equals 5 squared. And you might just recognize this already as a 3, 4, 5 triangle, but if not, we could solve. This is 25 minus 9. And so the opposite winds up being, opposite squared is 16, so the opposite was 4. 4. Okay. Having computed that, now we can compute the sine of the angle to be opposite over hypotenuse, 4/5. Okay. I don't know if I'll need this again. So that was something we've done before, but now we're going to put it in a new light where we're computing the trig of an arctrig function. So this is an example of what I was trying to put in the title, trig of arctrig. Okay, so what's going to be really helpful here is if you remember this general theme, the inverse cosine of 3/5 is an angle whose cosine is 3/5. Okay, so what you'd like to do is sketch such an angle and then take its sine. And I want to point out that's exactly what we did up here. Okay, so that's the translation that you want to make, right? This is exactly what we just did. But you have to recast it in that way. So maybe I'll put it in words. An angle theta such that cosine of theta equals 3/5. And that's exactly what we were given up here. Start with an angle whose cosine is 3/5 and compute the sine of it. Okay. So we'll try that for one more numerical example, and then we'll do one with a variable. Okay. So here's my triangle again. I'll write this in words. Remember, is an angle whose tangent is 3/2. Sketch it. Maybe I should give it a letter, but I guess I'm not gonna. Uh-oh. I better, because I think my machine was about to explode there. So that's going to be the angle down there. And we want its tangent to be 3/2. That means its opposite should be 3, its adjacent should be 2, and that'll allow us to figure out that it's the hypotenuse here. Maybe we'll just do this quick here. The hypotenuse is going to be the square root of 13. This is 2 squared plus 3 squared is 13, and we take the square root. Right? So now that we have our angle drawn, now we can compute the cosine. So that was copy paste. Cosine is the adjacent divided by the hypotenuse. All right. Last example then, and again this one is done with symbols instead of with numerical values. Oops. I need a new blank triangle. So I won't write it this time, just try to remember what we're doing here. This is an angle whose sine is 1 over x. So put the angle down here. I want the sine to be 1 over x. Well, I can make the opposite 1 and the hypotenuse x, and then I've done what I need to do. We need to solve for the third side. So a squared plus 1 squared equals x squared. And from that we can get that a equals the square root of x squared minus 1. So that is what's going to go right here. Right. And now having constructed this angle, now we take its tangent. I'll go ahead and just call it theta at the moment. That would be 1 over the square root of x squared. Oh no. Minus 1. Okay, so that's it today, and we'll see you back for section 5.5.